Okay, so welcome back, folks. We're going to carry on now with the half cell voltage. So this is, again, thinking about each reduction oxidation reaction as involving really two halves. So one set of reactants will be reduced, and the other one's going to be oxidized. Even as we were balancing them, the first thing that we were going to do is to split it into two half reactions. So if we just think about those half reactions as independent things, that we can look at their potential independently, then it's going to be a lot more useful for us as we try to mix and match half cell reactions to come up with new galvanic cells. So instead of thinking about, well, is this reaction going to be the reduction or the oxidation half? All of these tabulated values are for the reduction potential of any half cell reaction that you might look at. So these can then be combined to obtain a standard cell voltage. And we're going to get to that, how it looks. But say if you go back into the appendix in your textbook or look it up online, what this might look like in practice is you'll see, say, a reaction either written out completely as something like, say, zinc 2 plus 2 electrons going to reduced to zinc metal, or that can be shortened to just talk about, say, zinc 2 plus as the ion with a straight line in between going to zinc metal, and that will have a reduction potential of negative 0.76 volts, okay? Something like copper will have positive 0.34 volts. Okay, so if you were going to check out a list of these half reactions, they would just be tabulated like that as they go down the line. So what these values are is their tendency for them to go through the reaction as it's written. So we're always writing it as the reduction reaction. We've said that the more positive the potential is, the more likely it is to happen. And that's still the case. So when we're looking at these and trying to compare them, what we want to know is the magnitude and the sign, and to say the more positive one in a set of half reactions is going to be the one that is the half that is reduced. The less positive one will then necessarily be the one that's oxidized. Okay, and what else do we say there? Also important to note is that these potentials are intensive properties, meaning that it doesn't matter how much of the material we're interacting. Okay, so whether it's one atom of zinc or one atom of copper or a mole or 1.5 moles or 50 grams, in all cases, it's still going to be the same reduction potential that we're going to use. So next we can see exactly how these are going to combine to come up with our standard cell potential. So first thing we would want to check is to look for the most positive of the two that's on the list. So let's say we're going to look at a copper and zinc cell. So the first thing we have to do is to decide which of these two values is the more positive. And obviously in this case, we have positive value is the more positive. But it doesn't matter if they were both positive, if they were both negative, whichever one is the higher one is the one we're going to go with as the reduction or the cathode side of the reaction. So there we have our cathode is copper 2 plus 2 electrons going into copper. And that is 0.34 volts. Okay, and then we have the less positive one is then going to be our anode. And for that, we just turn it around backwards because we want the opposite reactions. Now we're going to have a zinc metal being oxidized into the zinc 2+ ion plus 2 electrons. And since we're doing the reverse reaction, we also have the reverse sign. So this is now 0.76 volts. And when we take the balance on the reaction, we find that copper 2+ plus zinc metal changes into copper metal and the zinc 2+ ion. And the overall voltage of the cell generated by the cell is 1.10 volts. Okay, so that's how we're going to add up the half cells again. So we see that the sum of the two half reactions and their potentials gives the standard cell voltage. Okay, I don't know why that traveled down the page with us, but that's fine. The easier way to write this down is to just look directly at the standard cell potential as the sum of the cathode minus the anode, or the more positive one minus the less positive one. In that case, in most cases, we should then be able to get to something that has a positive cell potential, and that's what we want for a battery. So if we're going to fill this out for the example that we just saw, the cathode was copper at 0.34 volts minus, and here we're just going to write it exactly as we would find it in the table, because that minus sign is doing the work of turning around the reaction for us and reversing the sign, right? So minus 0.76 volts. And we get the same answer as above, naturally 1.10 volts on the cell. Okay, so moving on. As with a lot of thermodynamic properties, we can't really measure absolute values for these things. We have to look at their relative values. So when we say 0.34 volts or negative 0.76 volts, that has to be compared to something. We need a zero because nature doesn't define a zero for us. So the zero that we've just chosen arbitrarily is for the reaction 2 electrons plus 2 hydronium molecules into hydrogen gas plus 2 liquid water. Okay, that is by definition, the half cell voltage is 0.0 volts. Okay, so that's what our reference potential is. And if we use this now as the half cell, anything we use as the other half cell tells us its standard potential directly. So we'll see how that works. I guess before we do, we'll mention that the hydrogen can't really be used as an electrode itself, right? It has to have a place to happen. So what we do there is just use the platinum electrode as a surface on which this thing can occur. And we tend to write that down as just acknowledging the platinum is in the room, even though it's not participating as a reductant or an oxidant, okay? So we'd write that down in the short form of the reaction, H3O+, the straight line, into the reduced form, hydrogen gas, another straight line, and then just writing down what we're using for a catalyst surface. Again, it doesn't participate in it, it's not doing anything special, it's just we're acknowledging that it's there. What else do we say about the half cell standard? Is that instead of a concentration, we need to think about the pressure of hydrogen gas. So this will be at 1 atmosphere. And the concentration of the acid will be at 1 molar, okay? Like usual standard conditions. Good, so now we're ready to calculate some standard reduction potentials. So even as with class, this is a good place to stop and try these examples on your own before we go ahead and solve them. So feel free to pause it, but I'm going to carry on, of course, and solve the thing. So if we look at the first example, where we have 1 molar solution of copper 2+ ions, half cell attached to a standard hydrogen electrode, copper being observed to plate out. So when we say that it's plating out, that means that copper metal is forming, okay? Which also means that we had this copper 2+ reactant reducing into the copper metal, okay? So that means that if copper 2+ is reduced, then that's our cathode. And that can only mean that the other half of the reaction, so in this case, the hydrogen electrode is oxidized. And that's going to be our anode. And what else does the question give us? It gives us the measured cell voltage at 0.34 volts. So at this point, we can write down our equations. So we have the standard cell potential is the standard half reaction for the cathode minus the standard reduction potential for the anode. This is given to us as 0.34 volts. The cathode, so this is our question mark, right? That's our value for copper that we're trying to find. So we can write that as copper minus the anode, which is, again, by definition, 0.0 volts. Okay, so from then we can just see it directly that for our copper 2+ to copper, reduction potential is 0.34 volts. And it's kind of as simple as that. So if we wanted to write down the reaction in the short form, we go from where the electrons are coming from to where they're being delivered. So we'll write down the platinum first. Hydrogen, since it's being oxidized. Now we have what it's being oxidized to, the acid. A double line to mark that we're moving from one half cell to the other. And now the copper 2+ ion, another straight line, and copper metal is the final result. Okay, so that's how we'd write down, say, a short form notation for an electrochemical reaction. Okay, second example. We can use zinc this time, and say when it's connected to the standard hydrogen electrode, zinc is dissolved. So again, that's your clue that we're saying that we have a zinc metal electrode that is being dissolved into the zinc 2+ ion. Okay, so that means that this is going to be oxidized. And that now the hydrogen, which was the anode in the last case, is now going to be acting as the cathode. Okay. And again, here we have our E cell. And it's still going to be equal to the half reaction of the cathode minus the anode. So this is 0.76 volts equals, now the cathode is 0.0 volts minus the standard cell potential for the zinc reaction, right? So 0 minus that is 0.76 volts. So our standard potential for zinc 2+ to zinc must equal negative 0.76 volts, which we already knew it to be. And there we have it. So that's the value of using the standard hydrogen electrode as the other half cell is that we can just determine the standard reduction potential directly from using that reaction. Okay, and if the zinc and copper half cells are combined, which one is the cathode and which one is the anode? I think we've already answered this question. So we know that the copper is going to be the cathode because it has the higher potential. So that's the cathode. Why am I writing? And zinc is the anode because it just has the less positive value. All right, and before we wrap up this video, let's just let's do this one example. Looking in a galvanic cell, so 1/2 cell of a zinc strip dipped into 1 molar solution of zinc nitrate, and the second half cell, solid indium absorbed on graphite in contact with a 1 molar solution of indium nitrate. Okay, so the standard reduction potentials for the indium 3, so this would look like, let's get rid of that, try it again. So the standard half cell reaction looking for indium 3 plus 3 electrons going to indium. In the question is saying that's negative 0.3 volts. And zinc, as we've seen already, zinc 2 plus 2 electrons going to zinc metal is negative 0.76 volts. Okay, and now in this case, both of them are negative, but we're still looking for the more positive one to be our cathode, okay? So that will be the indium. So this is our cathode. And the other one, the other half, is necessarily the anode, okay? So we can still look at the standard cell potential here just by plugging in their values. So we have negative 0.3 volts minus negative 0.76 volts, which is equal to 0.46 volts, okay? So it's positive, it's a galvanic cell like it said, so we should end up with a positive value for the cell potential. Otherwise, there wouldn't be a battery, it wouldn't be spontaneous. So that's good, that's how we would expect it to be. If we were looking for the balanced equation for this, so just switch colors to make it a little bit more obvious. In the balanced equation, we still have indium 3 plus is being reduced. So we can leave that one in the direction that we have it written down already. And zinc as the anode is going to be reversed because we know that it's going to be oxidized. So let's write that one down as zinc going to zinc 2 plus 2 electrons. Okay, and running down the list, we have, for balancing this guy, indium, one indium, that's good. One zinc, those are good. So we've balanced every atom that's not oxygen or hydrogen. There's no oxygen or hydrogen to deal with in this. So the only other thing we'd have to do is balance the charge, which is good, and then balance the number of electrons between the two half reactions so that we end up with a balanced equation that doesn't show any electrons in the end. So we're going to do that by multiplying the top row by 2 so that we get 6 electrons. And we'll multiply this bottom row, the zinc row, by 3 so that we also get 6 electrons. And then we can cancel those out. So ending up, we have 3 zinc plus 2 indium 3 plus going to 3 zinc 2 plus and 2 indium metal. Okay, and if we were going to track the cell voltages along the way and sum them up as well, Just clear a little bit of space here. So for that top line, we know that the standard cell potential is 0.3 volts. The bottom line is turned around, so it's now 0.76 volts positive. And at this point, we multiplied the top line by 2, and we multiplied the bottom line by 3 in order to get a balanced equation. So what should we do to these potential values? Absolutely nothing at all, because again, they are intrinsic values, and they don't change depending on how much of the reaction we're doing. So those potential values remain the same, and we end up with exactly the same cell potential as we calculated before, 0.46 volts overall. Okay, so remember a couple of things there. When you're using the standard cell potential equation, just plug it in as they're found, and you'll end up with the sign for the anode going the direction that it should, just by virtue of subtracting the anode reduction potential from the cathode potential. And if you're going to be summing up the reactions like this, don't forget that these are in fact intrinsic values that do not change no matter how we balance the atoms. Okay, so in your notes, after this point, you have a list of standard cell, standard half reaction electrode potentials. Just going from the top, a very high positive one is going to more often than not be the cathode. And here down in the very negative range is more often than not going to be the anode. And again, this should make sense when you're thinking about the periodic table and electron affinity and electronegativity. Kind of all of those same trends about which ones are going to grab a hold and pull an electron towards itself, and which ones are going to quite freely give them away. We can find lithium, sodium down here at the bottom that are on the far left-hand side of the periodic table, and the halides from the right-hand side of the table being greedy with the electrons. Okay, so that's it for this one. We'll pick it up next time. Okay, thank you very much.